let's talk about Taylor polynomials. Now, when we have functions like sine x, e to the x, ln x, it's difficult to do lots of computations with them. So, if we could approximate these functions using a polynomial, let's call it p of x, since the form of polynomials are pretty simple, they're all just ax to the n, and you keep on adding x terms until you get some x plus c. These are really easy to do computations with. It's easy to take derivatives, it's easy to integrate, and so if we can approximate these complex functions using polynomials, we can do a lot more computations a lot more efficiently. And that is what a Taylor polynomial is. By just using one singular point on this function and its derivatives, you can make an approximation using a polynomial. So the way this polynomial is created is by using a polynomial where the derivatives match. That means if we're centered around some point c, we need, firstly, the points to be equal, so f of c has to be equal to p of c. Secondly, to get an accurate approximation, we need f prime of c to equal p prime of c, so that they're both increasing and decreasing at the same time. And if you want to get more and more accurate approximations, you just make the higher order derivatives match. So if we wanted an even more accurate approximation, we could make the third derivatives match. And so on and so forth. It's technically infinite. Now let's talk about how such a polynomial is actually created. First of all, we know that the function value needs to match. We know that f of c has to equal p of c. Otherwise, it wouldn't be an accurate approximation at all. So our polynomial function, which we're going to call p of x, starts with this point f of c. Because remember, all these approximations are centered around this point c, because we only need one point and its derivatives on this actual function. So some notes first. When we're writing this polynomial function, instead of just using x, we're going to use x minus c. Because remember, this function is centered around this point c. When we want to make our first derivative match, and when we want to say that f prime of c has to equal p prime of c, this is going to correspond to our first degree term. This is going to correspond to some coefficient times x minus c to the 1. So when we take the first derivative, this 1 degree term of x simply becomes a constant, or whatever coefficient is beside it. Every term beyond that, if we were to plug in c, would result in x minus c equals 0, and would therefore cancel out, and every term below it would be a constant, and so that would also go to 0. So the only thing in our polynomial that influences the first derivative is our first degree term. So our first degree term has to have a coefficient of f prime of c, and this will be times x minus c to the 1. Similarly, our second degree term will match our second derivative, so f double prime of c has to equal p double prime of c, and this relates to the x minus c squared term, because when we take the second derivative, we're going to get 2 x minus c to the 1, and then simply 2 times some constant. Now remember, there's a 2 here, so our coefficient is actually going to have to be f double prime of c divided by 2 to account for the 2 that comes down when we take the first derivative. Therefore, our second term is going to be f double prime of c times x minus c squared, because second degree, over 2. Our third term, if we use the same logic, it's going to relate to our third degree. So it's going to be x minus c cubed, it's going to become 3x minus c squared, and then 6x minus c to the 1. Now here, instead of dividing by 3, we have to divide by 3 times 2 times 1, also known as 3 factorial. Therefore, our third degree term is going to be f triple prime c x minus c whole cubed divided by 3 factorial. If we were to keep on going with the 4th, 5th, 6th degree terms, you would see that you would always have to divide by factorial. Keep in mind that 1 factorial equals 1 and 2 factorial equals 2. So I can say this is 2 factorial, 3 factorial, so on and so forth. Now, with this demonstration in mind, let's go over the general form. For a function, f of x, if I wanted a Taylor polynomial approximation centered at point c, then my Taylor polynomial, p of x, is going to equal, firstly, f of c plus the sum, because a polynomial is just adding up all the terms, of the nth derivative of f, evaluated at c, times x minus c to the n, divided by n factorial. And this makes sense, because for the first term, it was the first derivative of c. For the second term, it was the second, so on and so forth. So, starting at n equals 1, going on to infinity, or however accurate you want your approximation to be, you'll always take the nth derivative for the nth degree term, and to ensure that the derivative of p of x and f of x match, you have to divide by n factorial. Now let's go over an example. Let's find the Taylor polynomial for f of x is equal to e to the x, centered at x equals 0. Firstly, this means our c equals 0 when we're doing p of x, and let's really quickly rewrite the general form. So p of x is equal to f of c plus the sum of however many terms we want of f, nth derivative, x minus c to the n divided by n factorial. And now let's write out our Taylor polynomial. So firstly, we need to know what f of c is at c equals 0. So e to the 0 is equal to 1. Our Taylor polynomial, which is p of x, is going to start with 1. Now, the derivative of e to the x is just itself. So the first derivative, evaluated at 0, is also going to equal 1, and so will every derivative beyond it. It's all just going to be 1, plus x minus c, which is 0, so instead I'm just going to write x to the 1 divided by 1 factorial, plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial, so on and so forth. Because all the derivatives are just 1, all of our coefficients here are just going to be 1. Now we can actually write the general form for this. So we can say that this is simply the sum of x to the n over n factorial from 0 to infinity. This is what's known as the Taylor polynomial approximation for e to the x. Now technically there's another term you need to know. If c is equal to 0, so it's centered at x equals 0, this is known as a Maclaurin polynomial. Now there's no difference between a Maclaurin and a Taylor polynomial, just if c is equal to 0, that's what it's technically called. So this is the general form of the Maclaurin polynomial for e to the x. And this will need to be memorized, along with two other functions which we're going to go over right now. So the other function is f of x is equal to sine x. Now, since we're going to need the derivatives to write out the first few terms, let's take them. So we have sine x, which is not a derivative. The first derivative becomes cos x, then negative sine x, then negative cos x, and then back to sine x again. Now we're going to find the Maclaurin polynomial of this, so we know that c is equal to 0, so let's evaluate all of these at 0. Sine of 0 is 0, negative sine of 0 is also 0, cos of 0 is 1, and negative cos of 0 is therefore negative 1. Now all we have to do is write out our Taylor polynomial. So it's going to start with f of c, which is 0, so we don't need to write it. Our first term will be this, so it's plus x minus c, which is just x, to the 1 over 1 factorial. This term is 0, so we're not going to write it. This will be our third degree term because it's 1, 2, 3, 4. And that'll be minus x cubed over 3 factorial. This term is 0. And if we were to continue, we would have cos x over here. So it'd be plus, as our fifth degree term, x to the 5 over 5 factorial, and so on and so forth. Now we can clearly see a pattern here. And so we're going to write this one as a sum as well. So let's write our sum. And the first thing to notice is that it alternates between being positive and negative. So the next term here would be something negative x to the 7 over 7 factorial. So because we have an alternate, we're going to start with negative 1 to the n. And then if you look at our powers of x, we go 1, 3, 5, 7, 9. So because we're taking all the odd numbers, we're going to write it as x to the 2n plus 1. And n is going to start at 0, ensuring that our first is 1. And since these powers line up with the factorial in the denominator, we're going to say that our factorial is 2n plus 1 whole factorial. And so this is the Maclaurin polynomial for sine x. The last function that you'll need to memorize is very similar. F of x is equal to cosine x. Since we're going to need the derivatives, let's take them. It goes from cos x to negative sine, negative cos, sine, cos. Now let's evaluate them at 0 because once again we're finding the Maclaurin polynomial, which means centered at 0. Cos 0 is 1, all the sines equal to 0, negative cos is negative 1, cos is once again equal to 1. So a similar thing happens here. All of these derivatives, as we go on, will alternate between 0, negative 1, and 1. So this function is also going to be alternating in its general form. When we write out the actual polynomial, p of x, we're going to get 1. Now remember the degrees that they correspond to. This is 1, 2, 3, 4. We're not going to have a first degree term. We're going to have a second degree term, and it'll be negative, so it'll be minus x squared over 2 factorial, we're going to have a fourth degree term plus x to the fourth over 4 factorial, and extrapolating from this, we can assume that we're going to have minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial. All we're doing is expanding on this sequence. So from this, we can also write another general form. We can say that this is equal to the sum, from n equals 0 to infinity of, because it's alternating, once again, we're going to have that negative 1 to the n term, x to the 2n, because here we're taking all the even numbers instead of the odd ones, over 2n factorial. And this is equal to cosine x. Now, there's another way to memorize both sine and cosine, and it relies on this principle. If I have a function that is the sum of something, so from n equals 0 to infinity, we'll say f of x is equal to x to the n over 2n. If I wanted to find the derivative, so f prime of this function, it would be d over dx of the sum, which is also equal to the sum of d over dx of this function. So remember this principle. The derivative of a sum is equal to the sum of a derivative. And this makes it a lot easier, because now my f prime of x is just another sum, where it's nx to the n minus 1 over 2n equals x to the n minus 1 over 2. Now, importantly, this not only works with derivatives, this also works with integrals. So if I had the infinite sum from 0 to infinity of x equals n, and I wanted to find the integral of f of x, I could take the integral on the outside, or I could simply rewrite this as the sum of the integral of x to the n, which becomes the sum of x to the n plus 1 over n plus 1. And this is equal to the integral of f of x. So we know that if we were to write sine x as a series this way, it would be the infinite sum of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And if we wanted to find this one for cosine, we could just differentiate the sum for sine. So this is going to be equal to the sum of d over dx of this whole thing. Now, anything that doesn't directly have an x in it, it's going to be a coefficient, so we can ignore it. The only thing that really matters is this term. Therefore, we're going to have the sum of negative 1 to the n over 2n plus 1 factorial. And here we're going to bring down the coefficient, so 2n plus 1, x to the 2n plus 1 minus 1. And this 2n plus 1 is going to cancel out with this, because remember, 2n plus 1 factorial is just 2n plus 1 times 2n factorial. So that's going to cancel. And what we're left with is negative 1 to the n, x to the 2n over 2n whole factorial. And of course, it's the infinite sum. So this is the same as the power series that we derived earlier for cos x. And you can do the exact same thing. I could integrate this to get back to sine x if I wanted to. Now, these techniques of differentiation and anti-differentiation are really important when you want to represent functions as power series. And what this means is that you go from f of x equals something in terms of x to a power series where you have something in terms of x and something in terms of n, from 0 to infinity. So what we're doing essentially is representing functions as infinite sums. Now, the most obvious example of this would be the function f of x is equal to 1 over 1 minus x. Now, this exactly resembles the geometric series formula, where if I had a geometric series or a geometric sum of a geometric sequence r to the n, where, the magnitude of r is less than 1, the infinite sum could be represented by 1 over 1 minus r, right? A of 1 over 1 minus r. So this in itself can be a function where our common ratio r is equal to x. So if we were to write this as an infinite sum, it would simply be the infinite sum to infinity of x to the n. However, with that previous example, that formula was only valid if the magnitude of the common ratio was less than 1. And so we say that the interval of convergence, which is simply the range of values of x for which this equality holds true, is from negative 1 to 1. And the radius of convergence would be 1. How would we find this radius and interval of convergence for more complex functions? Well, this is simply an infinite sequence, and all we have to do is apply our convergence tests. The most common one is the ratio test, where we replace n with n plus 1, and we take the ratio. So let's do that right here. We'll have x to the n plus 1 over x to the n, and all we have to do is take the infinite limit as n approaches infinity, and see that this limit has to be less than 1 for the series to converge. So this is going to become x times x to the n over x to the n. These two cancel out. Now, since there's no more n, we don't have to worry about the infinite limit. So this simply states that the absolute value of x has to be less than 1. And this 1 is our radius, because whatever our point of convergence is, here it's going to be 0, we have to be within 1 unit to stay convergent. So the radius of convergence is going to be 1, and the interval of convergence is found simply by finding the solution to this, which we know is negative 1 to 1. Let's look at another function that we'll write as a power series. This one is x over 1 plus x squared. Now this I'm going to rewrite as x times 1 over 1 plus x squared. Because we're writing infinite sums in terms of n, anytime we take an infinite sum like from 0 to infinity, the value of x inside that sum is going to stay constant. And therefore, I can say that x times this infinite sum is going to be equal to x squared, because I can simply move the x within and without the sum. So here, I'm going to write this as a sum first, because this is what looks the most familiar to me, and then I'm going to move this x back into the sum. What about this is familiar? Well, I'm going to rewrite it once again as 1 minus x squared. And now it becomes apparent that this is once again a geometric sequence sum where my ratio is negative x squared. So this becomes the sum, from 0 to infinity of negative x squared to the n. Of course, times x from here. I'm going to expand this. This becomes the sum 0 to infinity x times negative 1 to the n, x to the 2n. Now, when I move the x back in, all I have to do is add 1. So this becomes the infinite sum 0 to infinity of negative 1 to the n, x to the 2n plus 1. And this is our power series representation of this function. Now let's find the radius and interval of convergence, and we're going to use the ratio test once again. Now we have an alternating portion here, but because we're taking the absolute value of the limit, we can ignore it for now. So this becomes x to the 2n plus 3 over x to the 2n plus 1, because this would have been n plus 1, and it's the infinite limit as n approaches infinity. This has to remain less than 1. I'm going to rewrite this as x squared times x to the 2n plus 1 over x to the 2n plus 1. These two will cancel out, and now x squared, absolute value, has to be less than 1. Now this is going to have the same interval and radius of convergence, so it's going to be from negative 1 to 1, because anything beyond that and your magnitude of x squared becomes greater than or equal to 1. Now let's look at another problem. This is x cubed over x plus 4 whole squared. I'm going to do the same thing where I take the x cubed to the side, 1 over x plus 4 whole thing squared. Now, because this is squared, it makes it a little more complicated, but remember, we can use our derivatives and antiderivatives to simplify this and make it look like something we're more familiar with. Therefore, I'm going to rewrite this as x cubed times d over dx negative 1 over x plus 4. Let's clean it up a bit. This becomes negative x cubed times the derivative of 1 over x plus 4 is equal to negative x cubed. I'm going to factor out a 4 from our derivative, so what we have is d over dx 1 over x over 4 plus 1. Now, this is something that we recognize. This looks like an infinite sum for a geometric series where our ratio is negative x over 4. And so I'm going to write it as such. So this stays as negative x cubed over 4. This stays as the derivative, so d over dx. And this becomes an infinite sum. From 0 to infinity, our ratio is negative x over 4 to the n. Now let's clean this up and get rid of the derivative. So this becomes the infinite sum of negative 1 to the n, x to the n over 4 to the n. And because it's the derivative of this whole thing, I'm going to rewrite that as the sum of negative 1 to the n, because that doesn't change, times n x to the n minus 1 over 4 to the n. And all of this is still multiplied by our negative x cubed over 4 from earlier. So finally, let's put everything back into the sum. Becomes the infinite sum of, now this negative 1 and negative 1 here, so negative 1 becomes n plus 1. This times n, x n minus 1 gets a plus 3 from this x cubed, so x to the n plus 2 over 4 to the n plus 1. And this is our power series representation of this function. Now we still have to find the interval and radius of convergence. So let's do that using the ratio test once again. Again, I'm going to ignore all the alternating terms because it's the absolute value. So it becomes x to the n plus 3 over 4 to the n plus 2 times n plus 1. Now this gets divided by 4 to the n plus 1 over x to the n plus 2 n. Of course, this is the limit as n approaches infinity, but let's just write out the algebra first. This becomes x times x to the n plus 2 over 4 times 4 to the n plus 1. This is going to cancel out with these guys. So what we're left with is x over 4 times n plus 1 over n, and it's the limit as n approaches infinity. As n approaches infinity, this n plus 1 and n are going to reach a ratio of 1, so we can ignore it for now because it's just something times 1. So all we have to do is ensure that the absolute value of x over 4 is less than 1. Now this means absolute value of x is less than 4, and therefore our radius of convergence is 4. Since there's no addition or subtraction, we can assume it's centered around 0, and therefore our interval of convergence is from -4 to 4. We'll have to test the endpoints. Our sequence becomes -1 to the n plus 1, 4 to the n plus 2 over 4 to the n plus 1. When we do the subtraction, we're going to be left with 4 to the 1 times n. So our sequence becomes -1 n plus 1 times 4n. And this does not converge. It diverges by the n-term test, so this diverges. If we were to plug in -4, all that does is change the alternating sequence, and that still diverges, because -4 to the n doesn't converge either. Therefore, our interval is -4 to 4 with open brackets. Finally, let's do one more harder problem. This uses much of the same tricks, and it's x arctan -2x. Firstly, if we were to take the derivative of arctan 2x, it would be 1 over 1 plus 4x squared times -2. So we can write that the integral of this function is equal to arctan -2x. Secondly, we can also look at this -2 and move it outside the integral. So that's what I'm going to do right now. I want to say this is -2x times the integral of 1 over 1 plus 4x squared dx. Now, this form instantly becomes recognizable as our geometric sequence, where r is equal to -4x squared. So this becomes -2x integral of the infinite sum from 0 to infinity of -4x squared to the n integral with respect to x. And I'm going to expand this. -2x integral of the sum, -1 to the n. 4 I'm going to write as 2 squared, so it becomes 2 to the 2n, and x squared to the n, so x to the 2n as well. Integral with respect to x. Now I'm going to integrate. Remember, when I'm integrating, the only thing that matters is the term that has x, because I'm integrating with respect to x. So let's rewrite this. -2x times the sum, -1 to the n, 2 to the 2n, and x to the 2n plus 1 divided by 2n plus 1. Finally, all that I have to do is put this -2x back in, -2 and x. All I have to do is increase the exponents. So this becomes the infinite sum from 0 to infinity of -1 to the n plus 1, 2 to the 2n plus 1, and x to the 2n plus 2, all divided by 2n plus 1. And this is our power series representation for x arctan -2x. All we had to do was integrate, and the rest of our sum became apparent. Finally, let's find the interval and radius of convergence using the ratio test. So when we're using the ratio test, we can just ignore the -1 term, and I'm going to write this as 2 to the 2n plus 3, x to the 2n plus 4 over 2n plus 1 plus 1. Now we're going to multiply this by 2n plus 1 over 2 to the 2n plus 1 and x to the 2n plus 2. Let's write out the important components. I'm going to write this as 4 times 2 to the 2n plus 1. I'm going to write this as x squared times x to the 2n plus 2 this is going to be over 2 to the 2n plus 1 and x to the 2n plus 2. These will cancel out, these will cancel out. Now what we're left with is 4x squared times 2n plus 1 divided by 2n plus 1. Now remember, because what we're taking here is once again an infinite limit as n approaches infinity, the leading coefficient of both of these is 2. As n approaches infinity, the 2n here and 2n here are going to dominate the limit, and so this is going to turn into a ratio of 2 over 2 equals 1. And so this overall ratio is just 1. So this simplifies down to 4x squared absolute value has to be less than 1. Absolute value x squared is less than 1/4. This breaks up into x squared less than 1/4 and x squared greater than negative 1/4. Now the solution to this is just all real numbers, and when we solve this one, we get x is greater than negative 1/2 and x is less than positive 1/2. So our interval of convergence is negative 1/2 to 1/2. And once again, we have to test these endpoints to determine if they're open or closed brackets. Our radius of convergence will also be 1/2. Our radius of convergence will also be 1/2 because this is centered at 0 and it goes half a unit in either direction. So instead of x, we're going to plug in 1/2 and see if this sequence converges or not. We're going to use the ratio test once again. So I'm going to write this as, once again, ignoring the negative 1 term, 4 times 2 to the 2n plus 1, 1/2 squared times 1/2 to the 2n plus 1 over 2n plus 3 times the reciprocal, 2n plus 1 over 2 to the 2n plus 1 times 1/2 to the 2n plus 1. These all cancel. These all cancel. What we're left with is 1 over 4, 2n plus 1 over 2n plus 3. Now, as we take the infinite limit, so limit as n approaches infinity, this ratio once again tends to 2 over 2 equals 1. And so what we have is basically 1/4 has to be less than 1. This is true, and since our ratio is less than 1, this converges at x equals 1/2. Now, if we had plugged in negative 1/2, all that would have done was shift this alternating sequence 1 over, and because we take the absolute value in our ratio test, that wouldn't have mattered anyways. So we can conclude that the radius of convergence is 1/2, and the interval of convergence is negative 1/2 to positive 1/2, inclusive of both the boundaries.